Imagine a world where artificial intelligence doesn't just help us, it creates for us. A world where AI writes, designs products, discover medicines, and even help us live longer and cleaner. This isn't fiction anymore now in 2025. Here, I would like to introduce you to this fascinating world where machines are no longer just tools but also creators like us. First, to see where generative AI fits, let's zoom in. We know artificial intelligence or AI is the broad field focused on creating machines that simulate human intelligence. Within AI is machine learning or ML, which involves algorithms that learn patterns from data instead of being explicitly programmed. Deep learning is subset of ML where large neural networks with many layers can extract complex features. From deep learning emerges Gen AI, which consists of models that approximate data distributions and create entirely new contents. Inside deep learning and generative AI, we find large language models (LLMs). Those are trained on massive text corpora, optimized with billions of parameters, and capable of producing coherent human like language. So, LLMs like GPT are simply one type of generative model. Now, let's answer the big question: what is Gen AI? The word generative simply means to create new content like text, images, videos, or even audio. And artificial intelligence means that this creation is done automatically by a computer program without explicit human instructions for every detail. So, when we combine the two, Gen AI is the ability of machines to generate new content, not just analyze existing data. Formally, in AI terms, Gen AI is a subfield of AI focused on building models that can synthesize novel data instances statistically similar to the training distribution. For an example, if we train a model using thousands of cats, the model doesn't just recognize cat but it can generate brand new cat images that never existed before. I mean, in the training dataset. But still, it looks like real cat. If you think generative AI is not a brand new invention, for example, consider the example of Gmail Smart Compose from 2018. When you type hello, it suggests I hope you are well. That's Gen AI at work. The model looks at what you typed, then predicts the most likely next word based on the training data. Technically, it is modeling a probability distribution. So if you type I hope, the system knows that phrase like you are well or this email finds you well are statistically common. That's why we feel like computer is finishing our thought for us. This simple autocomplete feature is one of the earliest mainstream example of Gen AI. Another example you have probably used Snapchat filters and FaceApp all the way back in 2016. These apps could make you look younger, older, swap your gender, or even add a smile. But how it is working? Behind the scene, a Gen AI model is trained on millions of faces. It learns the statistical patterns of age, facial features, and expression. When given your photo, it doesn't just edit pixel, it actually generates a new version of your face, predicting you might look at 12, 24, or even 70 years old. And here is one more example: Google Translate before 2015. Back then, it was not powered by deep learning or transformers. Instead, it uses a method called statistical machine translation. What does that mean? The system looked at huge parallel corpora, millions of English Gujarati, English French, English Hindi, and other language sentences. It didn't understand the language; instead, it learned which word sequences in English were statistically most likely to map to word sequence in Gujarati. So when you type "I love my India," it wasn't reasoning like human translator. It was generating an output sequence based on probability labels learned from the data. That's still Gen AI. The system was generating new sentences, even sometimes the translation were awkward or incorrect. A part of these examples I still remember during my PhD around 2021 when I first heard about conditional gains being used in photonics design. For us, as a science student, it felt like magic. Suddenly, machine is generating entirely new nanostructure. This slide is from 2021, shows how Gen AI algorithm was applied to create metasurface hologram. Inspired by these results, I applied conditional GANs that same year for the design of acoustic meta-absorber. The idea was to directly generate absorber patterns from target acoustic response. Just like in photonics, AI started revealing novel absorber structures that we wouldn't easily imagine ourselves. So, all this means Gen AI was already around us, but it exploded in 2023. What exactly happened? A headline captured everyone's attention. OpenAI's GPT didn't just chat, it passed the exam at top law school business schools. Suddenly, the world realized this technology could reason, argue, and even compete in fields we consider deeply human. In March, in March 2023, OpenAI announced GPT-4, the latest version of its LLM. What made headlines was the claim that GPT-4 shows human level performance on many professional exams. From the bar exam in law to the GRE to advanced business school test, GPT-4 didn't just participate, it often scored above average human test taker. These two news marked a shift in perception. AI was no longer just an assistant for simple tasks, it was performing at a professional level in fields requiring reasoning, memory, and creativity. That's when the world realized Gen AI had truly arrived in our regular life. Many of you may have heard about this paper. Attention is all you needed. Although it was published in 2017, its impact has grown exponentially because it introduced the transformer architecture. It is the foundation of today's LLM models like GPT, BERT, and many others. On the left, you can see the authors and abstract of the paper. These researchers from Google proposed a simple yet revolutionary idea: an encoder-decoder framework built only on attention mechanism. On the right here we can see the architecture. The encoder, shown on the left side of the diagram, takes the input sequence and processes it using layers of multi-head attention and feed-forward networks. Each layer is normalized and connected to the next, making the model deep and powerful. The decoder on the right side generates the output sequence. It also uses multi-head attention but adds a special masked attention to make sure prediction happen one step at a time. At the very bottom, you will see positional encoding, which gives the model a sense of order because transformers don't process data sequentially like RNNs, recurrent neural networks. Finally, the output passes through a linear layer and a softmax function to produce probabilities for each next token. This architecture opened the door to today's Gen AI revolution, powering models like GPT, BERT, and many others. It is fast, scalable, and can handle massive amount of data, which is why this paper is now one of the most cited and talked about in AI research. We all are using ChatGPT. You can ask ChatGPT to write a professional introduction, for example, for LinkedIn, like this example here, where I tell it about my background in acoustic metamaterials, my love for travel and writing, and ChatGPT creates a polished bio instantly. You can also ask it for technical help. For example, here I asked ChatGPT to generate a simple Python code to build a neural network on the AutoMPG dataset, and it delivers in seconds. And of course, it can also be creative. I asked it to write a Gujarati poem about the monsoon in my state, Gujarat, and yes, I made sure it mentioned tea in the poem. Try it, it is really very good at such writing. ChatGPT didn't just grow fast, it became the fastest adopted technology in the human history. It reached 200 million users in just 2 months, the fastest than any app in history. TikTok took 9 months, Instagram took 30, Uber took 70, and even Google Translate needed 78 months. This pace of adoption is unprecedented. No technology before has spread this fast, not social media, not ride sharing, not even translation. And the reason is simple. ChatGPT tapped into something universal. Talking about two major types of deep learning. First is discriminative model. Think of it as a boundary drawer. It learns the conditional probability, the decision boundary between classes. For example, if we have blue and red points, the discriminative model focus on drawing a line that separates them. These models are mostly used for classification and prediction, trained on a labeled dataset. Examples of this model includes logistic regression and SVM. On the other side, generative models learn the entire distribution of each class. They don't just separate blue from red, they actually try to recreate blue points and red points themselves. That means beyond classification, these models can generate brand new data that looks statistically similar to the original. Example of generative models include GANs and conditional variational autoencoders. In summary, discriminative models classify and generative models create. Here is a simple example with roses. A discriminative model is like judge. You show it rose and it decide is this rose red or white. It doesn't create anything, it just classify. But a generative model is like an artist. It learns from the distribution of what red rose looks like and then it can actually create a new rose that never existed before. That's the difference. Discriminative models separate while generative models create. Now let's look at what happens when the input to a generative model is image. If the output is text, It can be used to write image caption or image description. If the output is image, it can be used as application for high resolution generation, image enhancement or style transfer. If the output is video, then applications can be image to video generation, motion prediction, cinematograph reaction and time-lapse generation. If the input is text and output is text, we get applications like translation, summarization, question answering, or even creative writing. If the output is an image, the same text can be turned into postcards, illustrations, or AI generated art. If the audio if the output is audio, text becomes speech, music, or even cloned voice. If the output is a decision, text can be used for tasks like game strategy or risk assessment. So, from one simple text input or image input, Gen AI can branch out into multiple modalities words, pictures, sound, and even intelligent decisions. If we step a little deeper and ask, how do Gen AI models actually learn the data distribution? Then it can be divided into two categories. First is explicit density model, second is implicit density model. Explicit, explicit density model try to learn exact probability distribution of the data. In other words, they do not only generate new samples but also know how likely each sample is. On the other hand, implicit density model doesn't calculate probabilities directly. Instead, they just learn to generate data that looks real. That's it. No maths. The best known example is generative adversarial network or GAN. Explicit density models are AIs that actually learn the full probability distribution of the data, and they come in two main flavors: tractable models that compute exact probabilities and approximate models that estimate them. We won't go deep into the math here, that's a topic for another video. Implicit density models can be divided in two major categories: generative adversarial networks and other implicit models. Till now, we have just seen how these incredible, powerful Gen AI models are built to understand and replicate the complex patterns in our data. But now, here is the important question: what happens when that understanding goes wrong? Or what if all this goes wrong? This brings us to one of the most important and talked about challenges in Gen AI today: the problem of hallucination. So, have you ever asked a chatbot a question and got an answer that sounds convincing, but is it completely made up? That's what we call an AI hallucination. It occurs when the model produces plausible sounding but false or misleading information. These are not intentional error but arise due to limitations in data or training. However, if you have used ChatGPT 5, you will find that such chances are far less compared to GPT 4. So we know hallucinations are a problem. But why does this incredible smart technology just make things up? It all boils down to one thing: the model is operating on incomplete information. It is not thinking, it is pattern matching. When the patterns are broken, so the output. First very common reason of hallucination is the model is not trained on enough data. If the AI was not trained on enough information about a particular topic, it doesn't know what it doesn't know. It just takes its best guess based on whatever similar data it has seen. Second possible reason is that model is trained on noisy or dirty data. We know the internet is full of biases, errors, and contradictions. If the model learns from this flawed data, it will replicate those flaws and answer that sound right but are based on those errors. Third reason is the model is not given enough context. If your prompt is overly broad, you are giving the AI too much room to invent. It is not being concentrated tightly enough to stick to the fact. One reason is one reason of hallucination can be the model is not given enough constraint. One reason can be overgeneralization, and this is big one. The AI is so good at finding patterns that it sometimes applies them too broadly, creating a stereotype or incorrect outputs. For example, it is like assuming penguin can fly because all birds can fly. So this is an example of overgeneralization. Hallucination can also happen due to bias or gaps in training data. It can also happen due to outdated information. An AI's knowledge is frozen at the point it was last trained. So, if you ask it about events or data after the point, it has no real information and is forced to hallucinate an answer based on old pattern. In short, hallucinations aren't magical, they are logical. If frustrating, results of the limitations in the data and the way these models work.